Welcome to the Computer Networks Lab. It is the 11th session of the circuit programming in C. In today's lab, we will be studying the I/O multiplexing or input-output multiplexing. So before introducing you to the input-output multiplexing, since we already studied the multiprocessing in the previous lab and we saw that the multiprocessing technique is still able to handle a lot of clients or multiple clients, then why do we need multiplexing technique despite of having a very fancy way which we studied in the previous lab? So firstly, I will introduce you to the I/O multiplexing. So what is I/O multiplexing? I/O multiplexing in circuit programming makes it possible for a single server process to serve large number of clients. Let us see it in this example. We have a server here and we have couple of clients like client 1, client 2, client 3 and then up to the client n. For instance, if we have an echo server, so echo server means that the client is going to send a TCP request to the server, and the server once get the any data coming from the client, it will bounce it back towards the client. As we saw in the previous labs, that the TCP server is able to handle only one client at a time. So to support many clients at a time, then we put some multiprocessing technique here. The server was able to respond to multiple clients as well. When any request is coming from the client, a new child process is born here, and that child process is then serving that client. So if there are like n clients connected to the same server, then n child processes will be born, and each child process will be distantly serving each client. In today's lab, we are studying some different technique, which is the I/O multiplexing. And I/O multiplexing, we are not caring about any child to be burned for each client, but instead, if there is data coming from any client, it should be relayed to the server. So let's first understand, if we have a multiprocessing technique, then why the multiplexing outperforms the multiprocessing. So I'll explain you all these and these 3 points. Frequent generation of process leads to poor performance. As I explained you in this example, if there is any client which is requesting to the server, and the server is creating a child process for that, and then that child process is dealing with that client. So if there are hundreds and thousands of clients there, and then hundreds and thousands of child processes are burned here in the server, then it will be kind of messy for the server to sustain it or to support it. And then the second is, it is not easy to implement because it has to be implemented considering the flow of multi-processes. Again, if we have like couple of clients created here, and then each client is connected with a child process of a server here, then there, as we saw in the previous lab, that either if you are using it in half duplex way, in half duplex way you need to have a very tight timing synchronization, and if you're using it in a full duplex way, then you have to have the separate pipe for each and every client. This separate pipe from one flow, which is from the client to the server, and then a separate pipe from the server to the client. So those things are very complicated, and it's like also computationally a bit expensive. And finally, we have the server implementation, because more complex in the situations where communication between the process is required. Owing to these limitations of multiprocessing, we have another way, which is the multiplexing. So let's first understand what multiplexing is. You may have seen this thing when you tie two cups with a thread, and then when you are talking in one cup and the other person is listening at the other end. In that case, uh, the other person can hear what you are saying. But if there are multiple cups and a single person has to hear from each and every cup, in that scenario, it will be cumbersome for the server to hear from each and every one. To make it more elegant, then you have to have all the cups connected to a thread, and then the thread will be tied together in such a way that there is only one outgoing path, and then here is a person and he is listening to a couple of cups. So I'm not sure if it will be working, but if there are like couple of people talking and each and every cup, then this person might be able to listen from this person also and also from this person. So in other words, when this person is talking, his conversation is being multiplexed here to the server, which is this person. And when this person is talking, then in that case, his conversation will also be relayed to this person. So both the talking or both the conversation will be relayed to a single person and he can hear it. So if you're talking about the telephones, then in that case, each and every subscriber have different resources. We have a single link which is outgoing and there are multiple clients at the input. So all the multiple clients data is waiting for only one single link to go, or we can say that there is a kind of parallel in and serial out. So all the parallel clients are waiting for their turns. Each one is multiplexed on that single line based on the resources allotted to it. So for example, the first client has been allotted frequency number first or the time resources number first. He will be given authorization to go through this link. After that one is transferred, then the next one will be given authorization and then he will go, and then the third client will go, and then finally the last client will go through that single line. So in that way, all the transmission from the multiple clients can be relayed on a single transmission line. Similarly, the data transmission and reception is also possible for multiplexing because it does not have to service with zero latency in real time. In real time, there are multiple subscribers there in the telephony system or any data transmission system. Ideally, they have to be transferred with zero latency, but that is not possible in practice because each one has to wait for its turn. So once the first one is transferred, then the next one will be transferred and the third one will be transferred. And likewise, all the data from the clients is transferred one by one in a multiplexed way, which means from parallel to serial way. Now the question is how to process and manage the multiple sockets. So when we have multiple clients there and the data is coming from the multiple clients at a time to a single server, then how are these multiple clients managed and processed? So we will study all these things in detail, but before diving deep into detail, let's see what's the IO model are. And we first examine the basic difference of the couple of IO models that are available in the Unix system, and which can be the blocking IO model or non-blocking IO model, or IO multiplexing, and there are also some signal-driven IO model or asynchronous IO model. So I'll explain here the blocking IO model, the non-blocking IO model, and also the IO multiplexing. As you can see in the blocking IO model, there is an application running and the application is requesting for a read. And this timeline of the application, you can see the process blocks in a call to read. When there is a reading process system call towards the kernel and there is no data ready to be read, since the data is not ready yet, so it has to wait for the data till the data is ready. Once we have the data ready there, then all the data is copied to the buffer of the application. When the data is copied to the buffer of the application, once the copy is complete, then it will return OK, and then later on the application will process the data according to its algorithm. In this case, the system call is blocked till the data is ready. The application has to wait for the data till the data is available for it. This kind of IO model is called the blocking IO model. The non-blocking IO model is a bit different. We have the application here and then we have a kernel here. So each time the application is requesting the system call or the requesting for the data from the kernel, if the kernel have no data there, then it will just send a kind of error, and that error is called would block. There is no data with me, you have to further wait for it. Then again the process will continue and the read process will again probe for the reading the data. With that system call, again it will check, and if the data is still not ready, again the kernel will respond with the would block. And finally, if there is some data ready here and if the read calls come there, the data is copied, and once the copying is complete, the OK is signaled to the application, and then once the application receives the OK signal from the kernel, in that case, it can process the data. From this timeline, you can see that process repeatedly calls read waiting for OK. So each time it is periodically sending some system call towards the kernel, and if there is no data from the kernel, there would be E would block message from there. And until and unless it has some ready data there, then the data will be relayed to the buffer of the application. It receives an OK from the kernel. In that case, it can just process the data. And this is the one which we are going to study today. And the IO multiplexing model, we have the application. It has a select function, and that select function will send a system call towards the kernel. Since there is no data ready, so it has to wait for the data, and once the data is ready, it will return a readable. Then the multiplexing will send a read command or a read system call towards the kernel, and that read command will leads to copying the data. Once the data is copied there, then an OK signal will come from the kernel to the application buffer, and then the application can process its data. So these three are very important. And beside these three, there are also like some signal driven IO model or asynchronous IO model, but that are not that important. So what are the steps which can be implemented for the IO multiplexing? To implement the I/O multiplexing that we will just see in some practical example, firstly, we have to configure the target descriptor for observing their changes. You have to first configure that particular FD or file descriptor for any changes. Once you configure it for the changes, it can be file descriptor 1 or the file descriptor 2 or the file descriptor 3. So you have to mention that my input console is, for example, the file descriptor number 1. And once you configure it as the file descriptor 1, then you have to consistently monitor or observe that particular console or the file descriptor. That is the second step here, which requests the changes in the observation. And finally, if there is any change observed at that particular console, then the data is read from there. So getting and confirm the response, which is the third step. So here are some details of how to configuring the file descriptor. Firstly, we have to set the file descriptor, and this set here is a data structure that is basically the list of file descriptor, and the list can be fd0, fd1, fd2 up to couple of them. So all these file descriptors are the data structure that is basically inside this set. As we have the set there, but there can be some garbage data from before. We have to reset it. To reset it, we have a command which is fd0 and set all the values inside the fds. For example, fd0 or fd1 or whatever they are, they will become 0. After we have 0 values there, then it's the time to configure it. And to configure it, we can configure any of the file descriptor depending upon our application. For example, if your input console is to be 1, then in that case, you have to put the index of that particular file descriptor, and then also the data structure that you have already defined here. In this case, when you set it as 1, since this is this index 0 and this is index 1, this will set or it will turn to 1. And when you put 2 here, then the next will also 0, 1, 2. So at index 1, which we did here, it was turn 1. Then at index 2, it also become 1. So as long as you require or you want to service the number of clients, you have to set their FD or file descriptor, and once they are set, they will be kept under observation, and that observation will then see any changes. If it happened there, it will be serviced. Finally, if you want to clear it with 0 again, then you can just mention the index of that one. For instance, if you want to clear this one, the index number 2, which is the file descriptor 20, then just put the index of that one, and then you can put a command fd underscore clear, and it will be clearing it. So here you can see the macros here and all the input arguments that are required here with also the description. Now let me introduce you to the select function call. For the select, please don't forget to put this one header file, which is sys/select. And since select is also using some timeout, so you will also definitely need times.h. So these two header files are both required for the select function. So inside the select syntax, then you can find couple of input arguments. The select function blocks the calling process until there is activity or any of the specified sets of file descriptor or until the timeout periods expires. The file descriptor specified by the read set argument are checked to see if they are ready for reading. And likewise, the write file descriptor are also checking to see if they are ready for writing. This except file descriptor are checking for exceptional condition. So exceptional condition does not mean errors are reported immediately when an erroneous system call is executed and do not constitute a state of descriptor. Rather, they include the conditions such as the presence of urgent message on a socket. The timeout specifies the maximum time to wait. The first one, the maximum FD, this is the maximum file descriptor that you are observing at the console. So the select system call tells whether there is any data to read on the file descriptor that you are interested in. So let's do a couple of examples using the IO multiplexing. In this lab, we are going to cover two examples. And the first example, we are going to see the function of the select function call and how it works. And once we understand the detail of the select function, then we will put all the IO multiplexing feature into the echo server, and then we will see how the echo server is reacting to multiple inputs, or how the echo server is reacting to the echo clients. So let's get started. Firstly, you need to go to that directory and then just make any file. For example, in my case, I have called it select.c. There is nothing inside it, so I'll start coding it here. As always, firstly, you need the header files. So here I will input all the header files that are required. So here these two header files are new. Since in the select file we are also using the timeout, so we also need the sys/time.h header file. Now let's define some buffer also here. And I believe the buffer size of 30 byte will be sufficient for us. And now let's begin the main program. As always, we have to return it with 0. And let's define all the variables. So firstly, I have to define the data structure with the command which we already saw, that is fd sit, and I'll declare two names here. Let's say the first one is reads and the other one I will call is just a temp or temporary. The next one, I'll also declare some integer for storing the result. So let me call it result. And also I will add an additional variable which is the string length that I'll use later on. And then I also have to define the buffer which I have already defined as 30 bytes. Now firstly we have to initialize the file descriptor set which is the reads here. So to do that we have to initialize it with 0 values. And then we have to define the standard input console, and let's say our standard input console is file descriptor 0. For that I will do something like fd underscore sit and the 0 console, and then also I have to define from where, so it is from read. I'll also comment it 0 is the standard input console. I want to make a program when there is no input there, then it should have the timeout condition there and it should just print that it's a timeout. However, when we input some text there, it should be echoed to us or it should be written back to us. So let's make something like a program that run for infinite loop. So to run something for infinite loop, we will need a while one. Now the variable that I have defined here, so it will just take whatever the value is there in the read. Sorry, this is not read, this is reads because I have defined it as reads. So I should use reads everywhere. So for the timeout condition, let me put the timeout for 5 seconds. So if I don't write anything within 5 seconds, there will be timeout. All these things, the structure has been defined here in the sys/time.h, and also since I don't have to define any range there, so I'll put this one variable as 0. Now the results variable that I have declared here, it should take the value anything read from this console. And to read the console, we need the select here. So I will just write the result is equal to select and inside the select, the first one argument is fdmax, so it should be greater than the one we have defined here. So it is 0, so I should put as 1. So until I don't have any timeout, just keep reading from the console, which is 0. And if nothing is written there, then there should be a timeout condition. So if there is nothing in my result, which means that if the result is equal to -1, in that case, there should be some error. And I can say that puts are, I can also say that printf. So it's up to you. You can write anything. So puts mean like put the string and write something like select error or anything. You can just notify that there is some error or something, and then double quotes, and then you just finish it with the semicolon, and finally you can break it right here because it's not meaningful anymore. And if there is no error or if the reads is not equal to -1, then in that case, if the read is equal to 0, which means that there is a timeout condition. So for the timeout condition, we will always have the result equal to 0. I'll simply put a timeout here. Timeout condition or just simply a timeout. So let me keep it simple. And else, if it is neither an error, for example it is neither -1, which is the select error, and neither it is the timeout condition, in that case I should be reading from the console, which mean that the console I'm observing there, is there any changes coming. So if there is any change, I should print it out. If it is set, then just read from there. So for reading, we have also put the string underscore length, and we can use it right here. And finally, I start the buffer from the 0, and then we can read all the length of it. And here I can simply print what is the message from the console. And the message from the console is %s, which is in the form of string. I can simply print the value from the buf that I have already declared there. I will finish it with the semicolon, and I will return with 0. So it is good to go, and now let's run it. And now I'll execute this select, and let me not type anything, and I'm going to wait for any timeout. So there is a timeout if I don't write anything for 5 seconds, because my condition for the timeout is around 5 seconds, as you can see in this one here. So my timeout condition is 5 seconds, so if I don't type anything, in that case I'll have the timeout. But in case I'm writing something, I enter it, it will be message from the console, and I will read it back. When I'm writing, it is storing into the buffer, and then I can read it. But if I again don't write in 5 seconds, then there will be a timeout condition. It means my select function is working properly. Now let's go to the echo server and implement all the IO multiplexing strategy in that program. And then we will see that how the IO multiplexing is able to serve many clients. So here in this folder, I have already put the echo client and the echo server. So this is just a simple echo server that we have seen couple of labs before. There is no multiprocessing, there is nothing. It is just an echo server. And we will just do all the changes that are required for the IO multiplexing. So let's get it done. We need the server socket, we also need the client socket, and then we have defined the buffer. So let's keep the buffer size 30, or let's keep it 100 bytes. And then again we need these variables, and then we have the server address and the client address. So all these things are required for our program. Now what we need to add, firstly we need to add the timeouts. For that one, again we have to first define the file descriptor set, and for that we have to use the fd underscore set as we did earlier. And let's define reads comma, and the other variable is copy read cpy underscore reads, or yeah, so that we can just copy it and this copy reads. And then we also have to have the timeout. So for the timeout, we saw that it should be in the form of struct. Here I can say that time value or timeval is the timeout. And furthermore, I also need to declare for the select, I need the fd max. So I should just simple declare it here, and then later on I can get the value for the file descriptor, and I can put it in this variable. So we will see it in a while, but for that we need a variable, and I can also declare this variable later on before that one, but it's a better way to declare all the required variable at the beginning of the program. So I'll say the fd max, which stores the value of the file descriptor that we are going to observe. I can declare the fd num. Let me call it BOF. I have been calling it buffer all the time, so let's call it BOF. So again, if it is not equal to -2, so we have already seen what this thing is. And then let's create the server and how the server is created. So let it be like the way it is. And then we are doing with the binding, and if there is any binding error, then it should give us the binding error. And then we are listening, and if there is the listening error, which means that this thing is equal to -1, then in that case we will have the error handling. So we have already defined the error handling, and I have explained you how this thing works, so let's not go into the details. From here on I will delete everything, and I would like to add some additional stuff that I need now. And those things are, for example, the fd0 that we just saw earlier. I have to do it now, so I have to initiate all the FD set from the zero value. The FD set, which I have called it uh, reads, yeah, I have called it reads. So I have to initiate from the zero value. So if there is any garbage value from the operating system, it will be just clear out. And I also have to specify which console I have to monitor. So the console is basically the server socket. So anything coming on the server socket, I have to monitor it. So that is, and here as I have told you that the FD max that I declared a while ago here is in the form of integer. So this FD max basically holds the value for this first input argument of the select. It should be the server socket file descriptor. Now I'll start my program with an infinite loop that we just saw earlier, so that we can keep running it forever. And while one is the one of the option, and I will just initiate it like this. And since I have already have the variable declared, which is copy underscore read, and it can keep the value from the reads here as a backup. Then I have to define the timeout here. Let's say my timeout is 5 seconds, and then also I can have the other range here. Here I have to feed the value in the form of the macrosecond. So 5000 means that 5 milliseconds. So also let me have a check on the select function, and if it is equal to -1, then I don't need it anymore because it contains nothing, and I'll just break it. Please remember this value should be more than what it is. So that's why we have added 1 with this one. And then here the timeout is also here. And if this value is equal to -1, which means that there is nothing in the select. So yeah, it means that it didn't see anything from the reading console, and that means that we have to break it because there is no multiplexing happening. And if this fd num is equal to 0, that means that there is a timeout condition. And even if we have a timeout, we are not concerned with that. So let's keep continuing it, or you can just say that there is print it and say that there is a timeout condition. So I don't need to put that timeout condition, and I'll just simply say that keep continuing it, keep repeating the loop. So given this console configured with this fdmax, I have to keep monitoring it, and if there is anything coming from there, I should just respond to it. I should just echo it. That's the reason I'll need a for loop for here. So it will start from the FD max. I think it should be +1. So it will start from 0, and it will keep incrementing until this value. And since it is less than this value, so it means that yeah, it will stop right at FD max. So the one doesn't make any sense. If you have to make it a is less than equal to, then in that case you have to just put the FD max. You don't need the +1. And right on the observed console, if there is a change, then we have to do this. And if this I is the server socket, which is this one, it means that there is a connection request. So to deal with the connection request, we have to accept the request, and then we have to update the FD max with that particular ID. And this will happens when this is running for the first time, or if there is any change in the connection request. So F will run. And if there is no connection request from there, then there will be the default else running there. So now in this case it means that there is new connection request, which means that a new terminal someone has opened and they want to access the same server. In that case the server has to multiplex his incoming messages, and to do that we will follow these steps. The client socket that we have already declared there, and we will just use the accept command that we know already. Since the client request has been accepted here, now we also need to put that client under observation. So we also need to put a condition here. If this the new client that is just recently added, we have to see that the file descriptor of that client is less than this one or not. If it is more than this one, we should update the fdmax with that file descriptor ID. If it is less than, we should keep this one as it is. And we also need to notify connection to the client has been added. So we need to see that how much clients are added, what is the client socket ID. We can do it here in this line. So as long as we are adding new clients at the terminal, it will be showing us there the client connection at that particular file descriptor has been added. And if there is no new client added, then we should keep reading from the existing client socket. And if there is nothing in it, then we have to just close the request. Clear out that particular file descriptor ID and also close that particular ID. So if there was a new connection request, just get that connection request, update the fdmax, and notify that there has been a new client added. But if there is no new request, then read from the existing client socket. And if any client is closed, if this thing becomes zero, which means that the terminal of the client has been closed, then right at that point, we also have to clear that particular client file descriptor, because it has to be used by someone else later on. And then we also have to close that particular client, and we have to notify that the particular client that was opened before has been closed now, because the terminal of that client has been closed. And if it is not closed, then when you read this one, just bounce it back towards the client, since it is an echo server. So read from the client and write to the client. So write anything coming from the client. So this line will write anything that is coming from the client, which means that it is an echo. And that is it. Then finally close the server socket, and then this is related to the error handling. So we are done with the program, and now let's go and test it. Let me rename it like select server, select, and serv. The name becomes very big, so I think this will be enough. And let's test it. I'll open a couple of console. The first console is for the server side, and then I'll open 2 or 3 for the clients. 1, 2. Yeah, please remember that the echo client is the same as before, so I don't have to go through it. Firstly, I'll create the object file for them. So for that, for the echo client, let's make the client, and also for the echo server, that is select server, echo SEL. So select server.c, and then I will call it as a server. Okay, that is done. So let me initiate the server like this with the port address 1234. It has been started. Now let me call that one from the client side. So I will, the client is this one, 127.0.0.1, and then 1234 is the uh, port number. So as I press it, there is a client connection request, and as you can see that it will update the file descriptor from this client, and the same way we will do it from this client as well, from this terminal as well. So I can say that it is the client, and 127.0.0.1 and 1234. So when I press it, you will see another request coming to that one. So the client number 5 is also updated, and when the client number 5, since this is more than this, so the fdmax will be updated with this value. Now the fdmax will have this value. Now we have two terminal running there, for fd at 4 and also fd at 5. So the for loop, when running it, it will move, it will keep observing for the maximum available clients we have. Now when I'm doing anything here, I can bounce back the effect from there, or the response from there, and likewise in the second terminal you can also see that that thing is happening. And when I want to quit from here, you should see that the client number 5 is closed, so I can also get a notification that I explained you before. And also if I quit from here, then again you can see that that client has been closed. Since the everything is clear, so if I again want to connect with that, that can be starting with that 4 because it was clear here. Since we are clearing it here, if you are initiating the request again, which is this one, then it will again allocate that particular fd to this one. If there is nothing added new or nothing closed recently, then it will keep reading the message. Whatever we type, it will be bounced back to us towards the client side. So this is how it works. We don't have to create any children process, but because of the IO multiplexing, we are reading from the console, and we are keep observing that particular console, and we are uh, getting the message from as many clients as possible. So that is it for today, and thank you very much for having your attention. Good night, since it's the night time, so good night to all of you.